Enhance. Enhance. Oh, hey guys. Let's get started with today's lab. All right, guys. So welcome to this week's lab. This time we're going to be covering projectiles, and so I'm going to go over a few pointers really quickly before we dive into the lab. So the first thing is what we've got here. So anytime that we're dealing with the Y component of any projectile, we need to incorporate gravity. So gravity for our purposes is going to be negative 9.8 meters per second. And so anytime you see A in any of the formulas, A is always going to be equal to negative 9.8 meters per second, and that's due to the acceleration due to gravity. So anytime also that we're dealing with any time to peak or from the peak to the final resting position, we can consider the Y value to be 0. And so if we look at some type of projectile motion, like this right here, we have some upward force that is carrying our object, and the entire time that the force is propelling upward, it's fighting against gravity, which we just spoke about as negative 9.8 meters per second. And so when the projectile is going up and up and up, it's going to consistently be slowing down due to gravity. And so when it finally reaches the peak position here, essentially for a very small amount of time, the value of the Y component is going to be 0, because it's the point where the upward force of whatever type that might be neutralizes with the force of gravity before it begins its ascent back down. So anytime that we're dealing with peak, either time to peak or peak is the beginning part of the problem, the Y component for that will be 0. And lastly, the point that I want to cover is Newton's third law, which talks about the equal and opposite reaction. So anytime that we're dealing with a propulsion and a braking impulse, if a question is asking the impulse needed to stop an object, so it's going some speed, and for that object to fully stop, the answer is going to be exactly opposite what you have for that. So let's say some object is going at 100 meters per second. The impulse that is needed to stop that is going to be negative 100. And that's due to Newton's third law dealing with equal and opposite reaction. So if there's a propulsion impulse and it's asking the braking impulse or the amount needed to stop, it's going to be exactly the opposite. All right, so now that we covered those few points, we can go ahead and dive into a few of these. I'm going to go ahead and do just a few examples from this page. I'm going to go over number 2, number 6, and number 9, chiefly because a lot of people have issues with number 6 and number 9 because they deal with a few different equations and components as well. So the first thing that we want to look at is the same thing that I was just speaking about a minute ago, about the from peak to landing. So we have a discus at 3.8 seconds to fall. So we have our time is equal to 3.8 seconds, and we need to find the VYF. So we already know that the initial velocity, since it's starting at the top, so the Vy initial is going to be equal to 0. And that again comes from, since it's starting at peak, it has a brief moment where its vertical velocity is equal to 0. So what we're going to use to solve this is we're going to use this equation here. So velocity is equal to the acceleration times the time. So what we end up with is negative 9.81 multiplied by the time, which is 3.8 seconds. And then that's going to give us our Vy final. So when we do the math for that, we end up with negative 37.24 meters per second. And so that's pretty simple. That's for the first bit. And you'll have quite a few questions like this on your test that relate to time to peak and time of descent from the peak. So I didn't mention this before, but one thing that's really important is you want to take all the information from the word problems that you get, and then you want to write that out somewhere on your paper so that you know what information that you do have and then what information you need, and then you can select the correct formula on the formula sheet to solve the problem. So for number 6, we have a diver with an initial height, so our yi is equal to 3.9 meters. Our initial vertical velocity, so our Vy initial, is equal to 4.7 meters per second. And we need to find the time. And we have our y final, which is stated in here as the time to fall back down to the same height of 3.9 meters. And then we also need the Vy final for this. So now that we have all this information, from this we can look at the formula sheet and figure out what formula is going to be best to solve the problem that we have. So when we look at that, we're going to see that this is the equation that suits best for this problem, and that's the Vy final squared is equal to the Vy initial squared plus 2 times acceleration times the difference in height, which is the y final minus the y initial. So now that we have this, we can go ahead and fill in our numbers so that we can go ahead and get the right answer. So the thing that we're looking for is Vy final, which is good because it's already isolated by itself on the left-hand side here. So now we just fill in the rest of the information. So our Vy final squared is equal to the Vy initial, which we have is 4.7 squared plus 2 times the acceleration, which, as I noted before, is always going to be equal to negative 9.8. And then that's going to be multiplied by the y final minus the y initial. And in this case, the y final and y initial happen to be the same value, which is 3.9. So one thing that you'll notice here is that you're going to get a 0, and then you're going to be multiplying by 0. So essentially the entire right side of this equation is going to be equal to 0. So we have our Vy final squared equals 4.7 squared plus 2 multiplied by negative 9.8 multiplied by 0. So what you get here is this is all equal to 0. So we end up with Vy final squared is equal to 4.7 squared. Then we just take the square root of both sides, and our Vy final is equal to 4.7. But since we are going downwards, since the diver is falling downwards, any downwards motion is always going to be a negative value. So since we're taking the square root of the number, it's not going to allow us to get a negative. So we just add the negative sign at the end here. So our final answer for this problem, for the VYF, would be negative 4.7 meters per second. Now we still need to find the time value. So in order to do that, we'll use another equation that you can find on your equation sheet, which is going to be this guy right here. So it's the Vy final is equal to the Vy initial plus acceleration times time. So now we just plug in our information here. We've got negative 4.7 that we just found is equal to 4.7 plus negative 9.8 times time. So now doing our algebra, we go ahead and subtract out 4.7 from this side. So we'll say minus 4.7 from both sides. And then what we're left with is negative 9.4 is equal to negative 9.8 times time. So now in order to isolate time, we divide both sides by negative 9.8. And then we end up with 0.96 is equal to our time. So that'll be our final part here. So now we know the time component to be equal to 0.96. And so that solves that problem. And in this case, it's a little bit easier to solve for the Vy final before we solve for the time. So for the last one, this is another one that a lot of people tend to have problems with, is number 9. So again, we're going to go ahead and write out all the information that we have. So we have the vertical leap, which is 1.2 meters. So that's our y value is going to be equal to 1.22 meters. So we need to find the Vy initial needed to get up to this height here. So that's what we're going to be looking for. And we have our y initial is equal to 0. So this one here is our y final. So our y final is going to be 1.22 meters, and we need to figure out what velocity is going to be required to get from 0 meters to 1.22 meters. So what we're going to do for this one is we're going to use the same problem that we use, or the same formula that we used for the last example in 6, and that's going to be Vy final squared is equal to Vy initial squared plus 2 times acceleration multiplied by y final minus the y initial. So now we just fill in the bits of information that we have here. And so since we're only looking at time to peak, so we're looking back at time to peak again. And so we're starting out here at 0, up here to 1.22 meters. And since this is the final bit that we're looking at, we're only looking at the time to peak here, we can go ahead and assume that the final y velocity at this point here at the height of the peak is again going to be 0. So we have 0 is equal to the Vy initial squared plus 2 times acceleration, which is negative 9.8, multiplied by the y final, which is y final minus the y initial is just the 1.22 meters. So now we just go ahead and do the math here, and we get Vy initial squared minus 23.912. So, and then that is equal to that's now equal to 0. So now we need to isolate the Vy initial, and the way that we're going to do that is add it to the other side. So then we get Vy initial squared is equal to 23.912. And the reason this is positive now is just because of the algebra to switch the sides here. So now the next thing is we just take the square root of each side, and then for that we end up with the Vy initial is equal to 4.89 meters per second. And so that'll be the final answer for number 9. And the reason I covered those problems is because they involve taking in certain assumptions, and those assumptions being, again, knowing that at time to peak, that the vertical velocity is going to be equal to 0, as well as knowing a few other components as well. All right, guys, so that wraps up the projectiles lab. So that's all for right now. I will see you guys next week.